Still people coming in?
I think we've stabled on the
Okay.
numbers of people, so I think we can start now.
Yeah.
So hi everyone, thank you for coming to today's COMET webinar. Our speaker is Dr. Mark Bemelman. So Mark is a recent graduate from the University of Bristol, where he completed his PhD that was focusing on the use of high-resolution SAR data for volcano monitoring, which is what he'll be talking about today. And since finishing, Mark has moved back to the Netherlands and is now working at SkyGeo as an INSAR consultant. So the talk will last around 40 minutes with plenty of time for questions afterwards. So if you have any questions, please put them into the Q&A as we go, and we'll come back to them at the end of the talk. So I'll hand over to Mark now, and then we'll get back to it.
Yeah, thank you, Edna. Yes, as mentioned today, I will talk about the use of high-resolution remote sensing, mostly SAR for volcano monitoring, as that's been the focus of my PhD. I do need to click still. So first, an important question to answer is, why would we monitor volcanoes in the first place? And I think this is fairly obvious for a lot of people, but they threaten life. For example, the Krakatoa eruption in 2018 killed over 400 people and injured over 7,000. They can also cause a lot of damage to infrastructure, such as the Hunga eruption and the La Palma eruption in recent years, that destroyed many buildings or destroyed communication cables, which amounted to large damages. And I think the best example of that might be the Eyjafjallajökull eruption in 2010 that caused nearly $5 billion in damages, mostly because of the effect on air travel across Europe. And so it is important to monitor these volcanoes for any signs of these very destructive events, right? Now, sadly, volcanoes don't really put up warning signs like you see here. That would make our job very easy. Instead, they give a variety of signals that might indicate that they're getting ready for an eruption. These could be ice melts, certain gas emissions, thermal signals. Earthquakes is a very big one. And the one that I'll be focusing on is the ground movement. As magma gathers below a volcano, it might cause the ground to inflate, and we can measure that at the surface. We can measure a bunch of these stuff with instruments at the surface. And a few as well with satellites. Now, for measurements at the surface, we need the instruments there. And that's not always the case. In fact, only about 1/3 of volcanoes that have erupted in the last 500 years have any ground monitoring at all. And so for the remainder, satellite data is the only data we can rely on. Now, how do we observe volcanoes using satellite data? Well, there's a variety of measurements we can do from satellites, and these tend to get grouped into 3 categories. On the right-hand side, we'll have the visual multispectral satellites. These are very good to track changes to the surface and gas emissions. So from, for example, an eruption plume, as you can see there. These are also great to see visual changes on the surface through like satellite imagery that you might be used to from, let's say, Google Maps. Then in the middle here, we get into the infrared stage. Particularly the thermal infrared is very useful to detect, for example, lava flows, or if they're present, thermal features just before an eruption. And then all the way on the left-hand side, near the radio and microwave spectrum, this is where we get radar, and more particularly SAR, synthetic aperture radar, which can get us surface changes as well, but also ground deformation. And the great benefit of INSAR or SAR is that it works at night and through clouds. So no matter the atmosphere, we will be able to reach the surface and get an observation there. Now, all of these things operate at a different resolution. And so when I say I give a talk about high resolution SAR data, I should quantify that a bit. When we're talking about those gas detections from those like plumes, for example, right? If it goes through specific compounds like sulfide gases, then your resolution is going to be much poorer than, for example, the radar data. right? So here you can see for the gas detection, you're measuring with pixels the size of kilometers. When you're looking more at the optical spectrum, it gets better. You get to be between about 10 and 1 meter. And these both tend to be observed somewhere between daily and weekly, right? Or also daily for some optical satellites. And then the SAR satellites is where you get a big spread as well. So you get very high resolution SAR satellite products, which have a pixel dimension about the same size as an A4 sheet of paper. These are very rare to come by, but can be very useful and are the type of data that I've worked with. A lot of you might be familiar with the Sentinel-1 interferometric wide, which is about 2.5 by 14 meters. And I gave some of this talk a few weeks ago where I walked that 14 meters, and I can almost guarantee it is bigger than the room you are in, right? Don't underestimate the size of a Sentinel-1 pixel. The timing between acquisitions can also vary a lot. Tends to be between 1 and 14 days that you will get a new acquisition to add to your time series. That's kind of shown here. While every individual satellite might vary between 1 and 14 days, if we were to combine all of the available satellites for this and really optimize our observation strategy, we could get several images a day. And if you do that, signals like these on the right will become much more frequent, like the signal observed from a dike intrusion in Iceland that covers just 1 day, or observations happening hours before an eruption, like the case of Agung, where the acquisition was 11 hours before the eruption, and is part of my research, and the case of Colima, where the acquisition was 7 hours before the eruption, and is the work of other SkyGeo employee, Jacqueline Seltzer. Now, my research here has focused on 2 Indonesian volcanoes, and it's not for any bad reasons that I focused on Indonesia, because Indonesia has got both a very dense population and a lot of volcanoes. And so in terms of metrics for exposure to volcanic hazards, so-called overall volcanic threat, it ranks far out the highest of any country, right? And so for that, I've focused on 2 cases, the Agung eruption in 2017 and the Merapi eruption that started in January 2021. In both cases, I'm looking at the precursory signal, and for Merapi, I'm also looking at some signals during the eruption. The Merapi eruption, by the way, is still going on right now. And I think some information on both volcanoes should appear right now, but these images might take a little bit to load. I mean, both volcanoes are stratovolcanoes, but as this information loads, hopefully, yeah, there it comes. Agung erupts much less frequently, about once per 100 years over the last 5,000 years or so. The last major eruption was in 1963, but about 50-something years later, it experienced some unrest again in 2017 that sparked the evacuation of over 100,000 people. And some months later, the eruption happened in November 2017 and lasted for about 2 years. And for this volcano, I'm particularly interested in a signal that was spotted on the crater floor of the volcano. Now, for Merapi, this volcano erupts much more frequently, about every 2 to 6 years, and varies between very major explosive eruptions and some more minor volcano dome building eruptions. The last major eruption was in 2010, and it has had several small dome building eruptions. Since then, the most recent one began with seismic unrest and deformation observed from the local monitoring network in late 2020, and the eruption started in January 2021. Here I'm looking at very strong deformation on the west and northwest flank of the volcano, and this is so strong that the INSAR method most commonly used was not really suitable here, so I had to go to different methods to detect this rapid displacement. Well, first, let's talk about Agung. So this kind of began off of work that was done by Fabio and Albino that looked at a dike intrusion between Agung and Batur. This was the cause of the major seismic swarm that happened in 2017, as you can see here in the histogram. And this intrusion also caused some deformation, as is seen here in this north component of the GPS station nearby. However, my interest was really focused on the summit, where we saw several phreatic explosions happening around the same time. And what is notable here is this gap between increased seismic activity and displacement and the eventual eruption, these vertical lines here, with very little activity happening just before the eruption. Now, looking at the summit crater, I was working off of the interferograms that were made that discovered this signal. These are shown in the top right. And you can see here an interferogram in the middle, which has all of these bands which indicate displacement appearing on the right-hand side of the crater. Right? If you then look at the layout of this crater, this is where we see those fumaroles. So my initial thought was, this signal is related to those fumaroles. It's all the way to the side of the crater, also on the very steep crater wall. But I carried on for a little bit, and I created my first time series that showed indeed that while we have the seismic swarm, we also see displacement, these black dots, has happened in between this period. And curiously, a little blip here just before the eruption. I'll get onto that later. But first, I needed to solve a little problem. And that was, on the one side, from my very high resolution data, I was getting interferograms that looked like this. So I was able to recreate those interferograms that I had looked at before. But then I looked at Sentinel-1 data as well, since it's freely available. And that signal appeared in the middle of the crater. And now, apart from the resolution, the only thing that's really different here was the digital elevation model that I used. And so it actually turned out that an error made its way into my processing because of this DEM. And to show why that was caused, here at this top black line, that was the DEM I was using that created the signal that was shifted to the eastern side of the crater. For the Sentinel-1 data, I was using this dashed dotted line that shows a 200 to 400 meter deep crater. And that difference in elevation of that lacking summit crater shifted the signal to the side of the crater. I was able to correct for this by having a high resolution DM made for me from other satellite data that included this summit crater. And with this very bespoke processing, really, I was able to shift the displacement in my high resolution processing so that maximum displacement appears in the middle of the crater. And this really changed my interpretation. Now it's not just this fumarolic field that's acting up. Now it's really the whole crater floor that's being pushed at from below. And so another thing I would like to point out is that to get this high resolution data, it requires a lot of bespoke processing and data that's not often available for volcano monitoring. It's very high resolution Cosmos, COMET, or TERRAS or X data. What we usually get to work with while discovering signals is automatically process Sentinel-1 data that tends to be at about 90 to 100 meters resolution. And in that signal, in this red box, you do not see the signal at all. And you would be perfectly happy to report this volcano is not doing anything particular. Whereas in fact, what's hiding in between those pixels is this whole signal here, which amounts to about 15 centimeters of line of sight displacement. And that I show here. So I did a time series analysis of the Cosmos, COMET, and Sentinel-1 data. And that showed two periods of displacement. One in September and October during the time of this seismic swarm and therefore the dike intrusion. That amounted total to about 12 centimeters of line of sight displacement and covered likely most of the crater floor. We do not have good data on the eastern side of the crater floor. But more interestingly, maybe, is this signal that happened days before the eruption. So this signal here, amounting to about 3 centimeters of displacement, was beautifully captured by one of the interferograms, has a slightly smaller footprint and happened within about 4 days of the eruption. And this was one of the few signals indicating the volcanoes getting ready to erupt. Now, I also then went on to model this deformation source to get a sense of its properties. And to do that, I couldn't just ingest all of the SAR data, because that comprises hundreds and thousands of points, too much for the computer to handle. So I had to subsample that. And there I chose to subsample very heavily outside of the crater floor and choose a denser grid inside. So I capture my signal of interest in more detail. I applied some simple elastic half-space models to this data and found that kind of two sources. So on the one side, the penny-shaped crack, and on the other side, the sub-horizontal sail, right? Both are basically horizontally extensive pressure sources that expand in the vertical, that these performed almost equally well. And therefore, I think that this source that I'm looking at for this signal is likely horizontally extensive and exerts its pressure in the vertical direction. The depth of these sources are also about 150 meters deep. So we're looking at something very shallow. And given the lack of other evidence of magmatic sources, this is very likely a hydrothermal source. And so with all of that, I was able to come to this conclusion where during the time of this dike intrusion, magmatic gases and heat were able to travel to the summit of Agung, pressurizing this hydrothermal system, causing increased fumarolic activity. This then caused the slight more uplift and the start of the eruption when magma finally intruded into this hydrothermal system on the 21st of November. And a few days later is when lava was first observed on the crater floor, pouring from the crater created in the November 21st explosion. So some of the key messages that I got left from Agung was that the use of high-resolution SAR data is critical to detect and understand these pre-eruptive eruption signals that would go unnoticed in lower resolution data. It is very well suited for these types of shallow processes that we find, because they often leave a very small footprint signal. And also very important in this processing is a high quality DEM of similar resolution to your data to maintain both spatial resolution and accuracy of your results that prevents misinterpretation. Now, before I move over to Merapi, I first need to explain what happens when INSAR is not really enough. You can see in these images in the bottom right, as the displacement grows, these fringes that indicate displacement get closer and closer together. And at some point, they alias too much to be able to be resolved. And when that happens, you can really no longer use INSAR without making quite strong assumptions about the type of displacement that you're dealing with. And here in this figure on the left, I've tried to quantify that a bit more. This region outlined by the orange and red lines shows kind of the limits of detection of INSAR in terms of the signal strength, so the magnitude of displacement, and the signal width, the spatial extent of this signal. And these panels B, C, and D roughly align with these locations on the graph, where you have something that's completely resolvable, something that's kind of right on the edge, and you start to see this aliasing effect very clearly, and something that's completely beyond the limits of detection, where in this GPS timeline we have about 3 meters of displacement that has occurred over this time period. Now, this is also, to no surprise, happening at Merapi, and this is where INSAR was no longer really that useful to me, and I will show that later on. Instead, I started to look at the backscatter intensity, the amplitude data. And here's a little animation. And what you can see in there is, first of all, the lava dome appearing in the summit crater. That's very exciting to see. But what I also noticed was the shift in the position of old lava flows here, outlined in several colors, around the rim of the summit crater. And to track that displacement, I used a process called pixel offset tracking, where you track patterns in this amplitude data, see if they've shifted, and from that shift, you extract the displacement. And to do that, the resolution of your input data really is key. So if you're working with that A4 sheet of paper, you're able to detect displacement roughly on the order of that dimension, that A4 sheet of paper. If you're working with that Sentinel-1 pixel, you'll be looking at far coarser, like resolving power for this type of displacement. So resolution is key. Now, as you apply pixels to tracking, you'll find that it is quite prone to outliers. So here's a small section where you can see a displacement signal on this lava flow underlined in red, and a stable region where you see all of these dots that are not moving at all. But you will also see several outliers. They come kind of individually, but also appear as groups. And I wanted to get rid of as many of these outliers as possible. And the way I thought to do it was identify them from the data itself. You can see here on the side that the amount of outliers and the magnitude of outliers is largely dependent on the window size that you use. So the smaller the area is you're trying to match, the more likely it is you're getting these types of outliers. And so the next thing I did was I tried several different methods to identify these outliers. The simplest of them is the magnitude filter, where you simply say any displacement factor above a certain magnitude, I will treat as an outlier. Right? So that might be this red line over here, where anything above 2 meters is an outlier. But this doesn't really work if you're looking at a very small area with large displacements, as it would comprise a very small proportion of your image and might be treated as outliers. The next method I looked at was the absolute median difference filter. This looks at a region around a point and calculates the difference of that displacement factor to that of its surroundings. And here are some examples. So you can see that there will be low differences when the surrounding displacement factors are similar, and high difference when the surrounding offset estimates are different. So these were the two that I could kind of think of on my own and implement, but I also looked at what's available in the literature. And there are several methods that claim to identify outliers from this type of data. And so I try to use these as well. These tend to calculate some sort of distance metric from the data, often in multiple dimensions, not just 2 spatial dimensions. And then somehow identify where there is high density in the data and low density in the data, aiming to remove or claim, flag as outliers those areas in the low density regions. Right? So there's the local outlier factor that tries to do that, and there's methods that are based on clustering, and points not belonging to a cluster are deemed outliers. And so to be able to test these methods, I had to create testing data. And so for about a month, I sat down and I manually classified randomly selected offset estimates from my data. And so here's a few examples where we've got a point that's a stable inlier, it's not moving, and its area is not moving at all, right? We've got a moving inlier where this is part of a moving signal, or part of the signal of interest, and it's moving similarly to its surroundings, so it's an inlier. And then here is one of the grouped outliers. This red arrow belongs to a set of 3 or 4 arrows with very similar offset that is clearly different from its surroundings. And in this image, you can see several singular outliers as well, which I also flagged. In total, I created about 5,000 points of testing data distributed across the different window sizes that I tested. And that kind of looks like this. So you'll see in orange and red are the different outliers. And then in blue and green are the different inliers, where the inliers tend to are grouped around my signal of interest, as you'll see here. Now, to actually be able to test which method performs best, I relied on the receiver operator characteristic curves. And what you need to understand from this graph here is that this dashed line, that's pretty much random guessing. As you randomly guess, you will have an equal chance to guess wrong or guess right. And so that will create a straight line. However, if your method is better at random guessing and guesses right more of the time, or classifies correctly more of the time, it will shift towards this upper left-hand corner. And so in this case, the green method is better than the orange method. And you can quantify that by looking at the area under the curve, the AUC. The closer it is to 1, the better your method is. And so what I did was I tested all of these different methods across several different parameters that slightly tweaked the way in which they determined these outliers. And looking from this graph, there's a kind of a clear winner that jumps out, and that's this median difference filter, which has the highest scores, often close to or above 90% or like 0.9. And so that's the one I continued with to clean up my data. And when I did that, this is kind of the results. So from the pixel offset tracking, you'll get displacement in 2 directions, in the range direction and in the azimuth direction, or the flight direction of your satellite. And you can see here how filtering has cleaned up the data substantially, particularly for the small window sizes. Right, so we've kept most of these outliers out. Now, the next thing I did was I compared these different window sizes. And what I found there was that sharp boundaries in the displacement signal that I expect to be there, so across the edge of a lava flow, got shifted in these large window size estimates. And I think that's because the windows that you're using to compare, they have a substantial amount of data still in the stable area, which creates a strongly matching peak that starts to eat away at this displacement signal. To combat that, I tried to average over several of these window sizes. That not only removes most of the effect of selecting one particular window size, but tries to combat at this shifting boundary as well. When I use all 5, I get this slow transition across the boundary. That's not really realistic. I know there's quite a sharp boundary there, as it's visible in every single individual window size result that I used. So instead, I averaged only the 3 smallest window sizes. This gave me a sharp transition at the location that I was expecting it. And so that's what I used to move forward. So the key messages for using this pixel offset tracking or sub-pixel offset tracking is that it is very effective at measuring displacements that are on the order of the pixel size or larger, that we can easily identify and remove outliers with the absolute median difference filter, that you can restrict at least the dependence on the window size in your processing by averaging over several window sizes to give a robust result. And under ideal conditions with high resolution SAR data, you can get down into the centimeter scale precision, as is shown in these figures on the right. We go to the non-vegetated, the top one, you can see that we're down into the centimeter precision for our averaged results. So we're looking down here. Now we can finally talk about Merapi. So Merapi has quite a dense monitoring network around the volcano. So there's lots of seismometers, these purple dots, and close to the summit, there's some instruments as well. But particularly the western flank of the volcano is devoid of these measuring instruments because this is very dangerous and very changeable area. You can see there's several lava flows in the past. And so that's why there's no instruments here. However, some of these electronic distance measurements reflectors here on the lava flow to the northwest were able to detect very strong displacements, and there was increased seismic activity. So the next thing to do was to look at the satellite data. Oh yeah, sorry, before I get into it, here's some of that data actually. So we can see the increased seismic activity just before the eruption, which is this second dashed line. And we can see the very strong displacement signal that was measured from the local monitoring network. Then at this dashed line, the eruption starts and we can see lava domes grow. There is this second period where we see some more displacement during the eruption, and that levels off again, where also the growth of the lava dome seems to level off. If we put these displacement signals in comparison with some other satellite observed displacement signals, we'll find that they are some of the highest magnitude and highest rate displacement signals currently observed with satellites. And here is finally what those interferograms are looking like. I know you've been wondering. you'll see that there are places where we can actually get some nice fringes that we might be able to resolve. But in other areas, we see some of the fringes, but they very quickly become decorrelated into this area closer to the summit, where we expect very high displacements from our local monitoring instruments. Here's also the Sentinel-1 image for that, where we can see those same fringes a bit further out, but close to the summit, it's completely gone. The correlation, the coherence is completely gone. We can't really use this signal, this INSAR, to resolve our displacements. And so we move over to pixel offset tracking. Now, when we do that, we get very nice, clear results closer to the summit of the volcano, where we can track the displacement on several of these lava flows. And when we do that, we can see that a lot of the places have these 2 periods of displacement also observed by the electronic distance measurements. Some of them go beyond 20 meters, right? So we're looking at very strong displacement. However, some other areas, particularly further out, here to the west, they do not have the second period of displacement, only active during the first. Now, I compared this data, this displacement data, to topography data as well. And I found that changes in the rate of displacement tend to happen around changes in the slope. And this is indicative of flank instability. Also to note was using one of the electronic distance measurement points, we were able to estimate the 3D displacement. And this is oriented almost entirely downslope, which is again indicative of kind of flank instability, landslides, that type of thing. All right. One of the other things we can see in here, so going back, is that each of these lava flows kind of goes at a different rate and also in a somewhat different direction. And so they kind of act almost independently, sliding past each other. And so this is the interpretation I ended up with for Merapi, which is that we've got a period just before the eruption where things aren't really moving that much. If they are, they're very slow. Then in the lead up to the eruption, we get a lot of seismic activity. Magma is making its way to the surface. And we see kind of displacement of these lava flows near the summit that move a lot, but also lava flows further downslope that don't move as much, but still move regardless. And so I'm thinking that this is caused by kind of stacked layers that slide over each other. And this would fit with the general structure of these types of volcanoes, where you've got lava flows on lava flows that have these natural planes of weakness. As we continue, we get into this lull where not much is moving and the lava domes are growing. Then the lava domes kind of stop growing and we get more seismicity again. This triggers more sliding of these lava flows on the western and northwestern side of the volcano. And that eventually too kind of weakens as well, where the seismicity remains a little bit elevated from what it was before. Now, some of the key messages that are added here is that the use of sub-pixel offset tracking can get us centimeter scale precision and get us deformation in areas where INSAR would fail. And so it's really very useful to use both INSAR and sub-pixel offset tracking in these cases to get the best of both worlds, really. And particularly for Merapi, it is true that the western and northwestern flanks are unstable, showing flank motion related to volcanic activity, primarily the seismicity, as the type of seismicity that was observed is indicative of magma moving through the conduits, so in the shallow subsurface. One final thing I wanted to discuss is kind of the use of high-resolution SAR data in general. As for volcano monitoring, this type of data is far from available in every case. So looking kind of across the board, we'll see that from this particular set of satellites, only between like 15 and 42% of the volcanoes that have erupted in the Holocene actually get monitored by these volcanoes at all. The other volcanoes have no data whatsoever. Other satellite missions are slightly better. And we've got Sentinel-1 that has much more like global coverage, but that's at a much lower resolution. And so we're kind of seeing interplay of several different things here. That there's data access that's restricting a lot of users from getting to this data that might be collected. The data might not be collected because of the mission focus or the acquisition strategy of a particular satellite. And also, in more recent years, we've seen commercial SAR companies come into the scene that can provide very high resolution data, but of course come with a premium price. And that's what we're seeing here. So in the current missions, we're seeing a lot of commercial and a lot of restricted in terms of these satellite data. However, the future looks promising as we've got a lot of satellite missions that promise decently like high resolution SAR that is open and freely accessible. So I'm really looking forward to future missions such as NISAR and the continuation of the Sentinel-1 missions to look for more deformation signals at volcanoes. So the final key message that I have is that high resolution SAR data is currently underused at volcano monitoring, and that we really need to work together between observatories, data experts, space agencies, and this might even include future mission design to kind of get the most out of the satellites that we've got lying around and get the most out of this data to monitor volcanoes. And before I'll move over to a completely different topic, I want to just focus on these key messages here, so have them in your mind. The other thing I wanted to highlight is when I gave this talk a few weeks ago, I ended with a message to please be kind to others. And I've got some data kind of to back this up now. So there's some recent research from Sweden looking at over 20,000 individuals that found a very strong increase in the psychiatric medication and hospitalization of PhD students over the course of their PhD. And so what I really think is we need to get better as a community to try and limit this kind of signal. We do not want to see this, right? We want to see deformation signals at volcanoes. We do not want to see this. And so I'll leave you with a message from a Dutch song that some of you might recognize. Let's try to translate here faithfully. And with that, that's the end of my presentation. Thank you very much for listening.
Thank you, Mark. That was a really interesting talk.
I'll go back to those key messages.
Yeah, it's really good and really interesting to see the kind of the level of detail you can get through the use of high resolution data that you would otherwise miss. We have a question already in the Q&A, so we'll start off with that one. But just to remind people, if anyone else has questions, please put them in there now and we'll get to those. So I'll start off with that first one, Mark. So this is from Charles Forrester. He says, the Anna-Krakatoa eruption and flank collapse was well modeled and predicted by Giachetti in 2012. How do we overcome local and regional government resistance, as this appears to be a problem no matter how good our monitoring and predictions are? Quite a heavy first question, but what are your thoughts?
Yeah. So that's really a kind of social aspect to this, is how can we effectively message that that our message of kind of warning gets to the right people, and that inspires them to take action, right? Take the appropriate action. I think what is needed for this is kind of a closer link in the communication between the data modeling experts and the relevant observatories. So if you are working on a particular volcano and you're like modeling its behavior, or you're looking at these observations, try your best to include the local monitoring agency, government, whatever it is that might be interested in your work. Get them on board early so that they will be able to listen to your like results and be able to act on that. I think that's my recommendation here. Kind of gets to that collaborative effort between data experts and observatories.
Always a good thing to remember while you're doing the work. Kind of following on from that. So with kind of, I know you put a lot of work into these case studies. How would that translate then into kind of if there was unrest at a volcano now, how long would that processing take? Is this something you could do kind of in a response situation?
So now that so over the course of my PhD, I kind of developed methods to try and process a lot of this data as like automated as possible within the scope of my capabilities as a programmer and the research needed for my PhD. That being said, if I were to get a new set of data that is similar to the ones that I've worked with before, so for example, extending the time series of these volcanoes, I would be able to do that quite easily by just adding those to the relevant folders and running them. It might take a few days to weeks to, let's say, process another 1 or 2 years of the Merapi data, because that's very high resolution and requires a lot of like iterative steps. But that type of processing can be implemented into a monitoring strategy when you can talk to the people that are most interested in monitoring these volcanoes, so like the observatories. If they're keen to work together with you, you should be able to set up potentially a continuous monitoring effort for them.
Yeah. Right. So we have another few questions. So the first one is, how deep is the source of deformation at the west and northwest sector of Merapi?
Yes. So at Merapi, right, I show, so let's go back here, right? I showed this this graphic here, and in the scale here, it looks like it's about like several hundred meters thick, this dark blue section, and this very light blue section that might only be tens of meters thick. This is quite hard to estimate given just the surface displacement data and very little information on the like structural integrity of the volcano. At least to do it sensibly very quickly. What I did do was I looked at the kind of spatial complexity of the displacement signal and the fact that it really correlated with the edge of these lava flows and knowledge of the general thickness of these lava flows being in the range of 10 to 100 meters to estimate that at least what's moving here near the summit only really comprises this top few lava flows, so should only really be about 10 to 100 meters thick. For the area that extends further south, this is a lot less clear because we do not have observations over the whole area, right? You will see here that a large chunk on the western side is missing in our data. It's poor quality, so it's filtered out. But this could potentially be deeper and would require modeling. I think this is work that's currently being done in France, in Clermont-Ferrand, and I'm really looking forward to see what they find modeling the stability of Merapi. In the case for me, it was kind of a question of writing up the interpretation of the signal versus sticking all my remaining time in modeling, and was a consideration to kind of finish the PhD at some point, and we decided to not focus on the modeling and leave that to our colleagues in France.
There's always more that you can do. So we have a question here from Herlan from Indonesia, who says, nice talk. Which kind of follows on also from the question follows on from what you've just been talking about, is did you quantify the potential volume that may collapse due to a flank instability, and is it going to be a potentially very hazardous?
So my recommendation to the Indonesian observatories is to try and well, maybe not necessarily directly directed to them, but in terms of an estimation, the area that I found that's moving, I need to go back to the interferograms for that, yeah. So can kind of draw a little shape around that. Let's see, then can kind of draw a little shape around that. That is roughly speaking this area here, which is and it has a pretty well-defined boundary, at least on this northern side. The southern side goes through poor data areas with poor data quality, so it's not well defined. But on this northern side, this boundary is pretty clear and pretty consistent throughout the time period that I looked at. Whenever there was any slight motion on this deeper failure plane, it was always terminated at this northern edge. This comprises about 1.2 square kilometers of area, and so if we were to go by something that is about 100 meters thick, which would, in my opinion, but that's not based on any modeling, be a little bit of an underestimation of this thickness potentially. That would give around 120,000 cubic meters, I think it is, if my conversions are correct. It is not in the category of sector collapse, I would say, right? So this is much more much more aligned with kind of thin-skinned motion of several individual or few layers of lava flows than it is a full sector collapse. However, I would suggest kind of waiting on properly answering this question before getting results from like the modeling on the stability of the volcano.
Yeah, that makes sense. Just what someone was wondering here, why you chose Indonesia as your case study. Yes, there are loads of volcanoes around the world. How did you choose these two in the end?
So there's two reasons for that. So one is, generally speaking, Indonesia has got a high proportion of the world's active volcanoes. And I talk about this at the beginning of my presentation. And it has a high population density, particularly the island of Java, right? And so it brings about a lot of volcanic risk. Trying to go back to the slides. The other reason is a little bit more about like data availability. You can only really work on volcanoes where there is this kind of work where this kind of data exists. And it just so happens that these volcanoes have been monitored with high resolution data, and that they had a period of activity somewhat close to the duration of my PhD, so that I could look into this and provide kind of new insights by studying these signals. Right. So while providing the answer, I've finally been able to make it back to the slide here, kind of showing that Indonesia ranks highest in the world in terms of overall volcanic threat. And even if you use different metrics, it will likely appear in this top 20 list somewhere. And so it is quite a valuable location to study volcanoes in terms of the impact on humans, at least.
Yeah. So we have another question, which is a bit more, I think, looking at the differences between SPOT and SAR, and kind of looking at the SPOT is high resolution while SAR is not. I think it was a bit confusing. So if you could, a few words of clarifying.
Okay. Yeah. So I want to clarify that SAR can be high resolution in like every way of the word, right? So it still works that you can see small footprint displacement signals, possibly like in volcanic settings as wide as like a few tens of meters even, right? That has been observed before in volcanic settings. If you go away from volcanic settings, you go into urban areas, you can look at kind of within the 1 to 10 meter scale at deformation signals, right? We're able to resolve that as long as you have this high spatial resolution data. Where SPOT comes in, so the pixel offset tracking, is where the deformation is very strong. That's kind of the signal, you're no longer comparing the same pixel to the same pixel, because in one of your images, a pixel has moved to a different location. And you can when that happens, you can no longer use the in the interferometric part of INSAR as a method to resolve displacement. And you kind of need to resolve to more like almost rudimentary methods of looking at an amplitude image and seeing, hey, that moved, and trying to quantify that movement in there. I hope that that gave some clarification.
Yeah, makes sense. I mean, same data set, but different kind of case that you're looking at and scales.
Different processing to get at different scales of deformation magnitudes. Yeah.
Yeah. So we have a question here from Sylvan, which is, in your research, did you find any significant differences between the ground motion or deformation pattern between Agung and Merapi? And if so, how do these differences influence your approach to monitoring different volcanoes?
Yeah, so to give like a one-sentence summary on the deformation at Agung and Merapi. At Agung, we're seeing a shallow pressure source causing uplift on the crater floor in the order of magnitude of like 1 to several tens of centimeters. And in the case of Merapi, we're looking at flank instability and flank motion on the side of the volcano reaching over 20 meters over, like it's not exactly the same like time period, but in terms of displacement rate, they lie very far apart. And so this does influence your monitoring strategy. So for Agung, you can use INSAR. That's totally fine for those types of magnitudes. And that's really critical there to actually get a sense of these minor changes in displacement over time to be able to potentially model that further and get a sense of what is this very shallow subsurface doing before an eruption. And here we know that it is, at Agung, it can actually be quite sensitive just before an eruption, right? That signal that appears within the last 4 days before the eruption kind of indicates that displacement on the crater floor can be used as kind of a precursor to volcanic eruptions. At Merapi, we're looking at a signal that is likely triggered by the seismicity caused by the ascending magma. And this here really relies on the very high resolution SAR data and this pixels tracking to get the map data. But saying that, these few ground monitoring stations, the EDM data, can already get at the kind of magnitudes of the displacement. So if you're able to see a large signal in there, you need to look at your SAR data. But if that's not doing anything, then there might not actually be much going on. So my recommendation in terms of monitoring there is to keep enough data coming in to make sure you keep that coverage, right? Keep that spatial coverage so you're able to resolve a time series should you need it. That's kind of also the case for Agung and really any volcano. And that's going to change depending on how active your volcano is. If your volcano suddenly becomes much more active and gets stronger displacements, more changes to the surface, then you're going to need more frequent acquisitions. And so that might be where you would start requesting acquisitions from space agencies to happen whenever they can really, or in specific modes that might be able to get you to get more detailed data. So I hope that answered the question.
That was good. We've got a question here from Sammy, which is, can you use the same technique for example, geothermal modeling? So the deformation due to fluid change. So applying this elsewhere.
So in general, I would say yes. What we're measuring here is displacements at the surface. So if any kind of subsurface process that is able to cause displacements at the surface, which have, let's say, like a spatial extent of tens of meters or higher to like tens of kilometers, and from displacement magnitudes of So let's see if I can kind of show this in the limits of SAR plot. Displacement magnitudes down from like a fraction of a centimeter up to, in the case of spot, tens of meters tends to be. Let's see if I can get there. It should be here, yeah. So here we can see signal strength, right? We're looking at anything within this box here that's created for INSAR. And we can see that goes down to like fractions of a centimeter, all the way up to, if your area is large enough, even in the order of meters. And then for subpixels tracking, you get kind of a box that extends beyond here, where you can see larger signal strengths, but you won't be able to resolve very small footprint signals because you're working with this window size that you're using to estimate the offset. So if all your displacement happens well within that window size, you might not be able to track it. And so that kind of gives the detection limits. And to get back to your question for hydrothermal, I believe it was, if that is able to generate a surface displacement signal, you should be able to observe it as long as it falls within these bands and you've got the data acquired, right? Because for a lot of these volcanoes, it might be that none of this data gets acquired and you're still in the dark. So as long as you have the data and there is surface displacement, you should be able to observe it.
Right, so we have two last questions. So
yeah.
The first one I think you've kind of touched on before, which is the data from SPOT, can you use that for rapid monitoring?
So in theory, yes, right? So you can, so I made time series out of this, right? Let's see if I show that. I'll show that a little bit later. I made time series out of this, but of course you can, so let's see. Of course, you can also compare any two acquisition dates of the satellites, right? And do pixel tracking to kind of generate a map like this, just between those dates, and use that for kind of rapid monitoring. You're really relying on the when you get new acquisitions from your satellites. So in the case of this data, I used Cosmos COMET, which has acquisition kind of date differences between 1 day and generally 16 days, but they might not observe every time. So my average over the period that I looked at here in Merapi is about every 5 days, I would get a new image on average. For Terrace or X, it is going to be 11 days or multiples of that. And so on average there, I looked at like a mix between 11 and 22 days mostly. I think my average was closer to 20 days for that. So that would be your interval to get a new data point. And then you can compare what has the recent change been. And you can use that for kind of rapid monitoring, where as soon as the image comes in, you get it off the internet, you run it through your processing. And with my processing, something like that could be done within, let's say, an hour, right? Potentially half an hour. If you want just one offset map, that could probably be done within half an hour.
That's really, really cool. So we have a last question here, which I thought was a nice one to end it on, which is from a new PhD student who says, fantastic talk. I'd just be interested to ask Mark, what would be his one piece of advice to be for me just embarking on this terrifying but awesome PhD journey?
Yeah, I think my piece of advice is, I would say, look after yourself first and foremost, right? It is you doing this PhD, and you need to be able to rely on yourself to do this work. It can be very hard work. It can be difficult. You will get lost in the data, not knowing what to do next. But first and foremost, you should be looking after yourself, making sure that you are kind of in the best headspace possible to complete this task, and also don't be afraid to kind of ask for help when you definitely feel lost, right? There's people around you that want to help you, might not always be in the best position to help you, but will try and get you to a better headspace to tackle this this PhD, right? It is often, right, described as for most people one of the hardest things they've done, and so don't just underestimate that, but know that there's people around you that are there to help you.
Yeah, I think that's really good advice and nice thing to end on. So we just want to thank you again, Mark, for sharing your work with us as well. Thank you for everyone who came and asked questions. So right before we end the webinar, I'd like to mention that we have a next webinar planned to be on the 13th of November, which will be given by Stanley Yip, who is a postdoc at the University of Leeds, where he's focusing on examining how heterogeneity in the crust modulates ground movement. So we'll be sending more information about this at the end of the month. And also a reminder that you can access previous COMET webinars and COMET Plus webinars on the YouTube channel. So yeah, thank you again for coming and participating. Yeah, we'll end it there. Thank you.
Thank you.